Okay, so recall for the past few days we've been working with limits, and that just simply means as a sequence keeps on going on and on forever, where is it approaching? And that's basically the idea that we're working with now. Is basically if we see a series that just keeps on going on and on, we're not going to stop at any term number. We want to know, what is that sum really going to equal? And so we're going to be creating formulas for that. So let's take a look at this first series here, 1 to 2, 2 to 4, 4 to 8. We see that every single time we're going to multiply by 2 each time. So because of that, we know that this is a geometric series. So if we're trying to find the sum of each of these values here, the n terms, that's our most general, we want to find the sum given the nth term. Then we know that since it's a geometric series, that's going to be our first term times 1 minus our ratio, 2, to the n power, over 1 minus our ratio, 2. Simplifying that out, we get 1 minus 2 to the n over negative 1, and that simplifies out to give us 2 to the n minus 1 by distributing that negative 1 on the denominator. From there, we can just plug in our values. Let's take a look at letter B. That's 20 terms. So let's see what happens as we increase the number of terms. 20, 100, 1,000, and infinity. S sub 20, that gives us, here's our formula, 2 to the 20th minus 1. Enter that in your calculator. And you get 1,048,575. Letter C, let's do S sub 100. That's 2 to the 100 minus 1. That gives us 1.3 times 10 to the 30th, a really large number. Let's go on to D. We're going to increase it to 1,000 terms now. So we have 2 to the 1,000 power minus 1. And my calculator cannot handle it. It says overflow error, which makes sense. Notice how as we increase n, our sum gets larger and larger, and well, it just becomes too large. The calculator can't do it. So if we're looking for S sub infinity, well, if this is not going to give us a value, then we know that this is just going to infinity. It just keeps going on and on and on. All right, so let's take a look at our next example. Actually, this one was written incorrectly. There really should be like a plus 1 right in between there. So if we rewrite this, this is 3 plus 1/3 plus, oops, I rewrote it wrong again. 3 plus 1 plus 1/3 plus 1/9, and so on. Okay. That way this series will work. We see that every single time when we go from term to term, we would be multiplying by 1/3 each time. Okay, so let's repeat the same procedure. We first need to find S sub n, our most general sum. Since it's multiplying by 1/3, we know this is a geometric series. So, geometric series calls for our first term, 3, times 1 minus our ratio is 1/3, to the n power. And then that is going to be over 1 minus 1/3. 1 minus 1/3, well, that's going to give us 1 minus 1/3 to the n power, and 1 minus 1/3 is going to give us 2/3. So really, 3 divided by 2/3 is the same thing as 9/2. So we've got 9/2 times 1 minus, in parentheses, 1/3 to the n power. And that's going to be our simplified sum formula right there. Okay. All right, let's go ahead and plug in some numbers. Let's do B. B was to the 20th term, so S sub 20. So we've got 9 over 2 times 1 minus 1/3 to the 20th power. Entering that in our calculator, we get 4.499, roughly. That's an estimate. Okay. Letter C, we're going to plug in S sub 100 now. Do the same thing, 9 over 2. And 1 minus 1/3 to the 100th power is going to give us about 4.5. Letter D, 9 over 2 times 1 minus 1/3. This time is to the 1000th power. We will get about the same thing, 4.5. Well, look at that, 4.499, 4.5, 4.5. It's only safe to assume that if we go all the way to infinity, 1 minus 1/3 to the infinity power, we will end up getting about 4.5. Okay, so take a look at these two problems, number 1 and number 2. And the next question we're being asked here is, well, why does one infinite geometric series converge to a limit, a number, 4.5, but the other did not? It was going to infinity. Take a look at those two equations. Oops, not that one. Yeah, this one. Let's take a look at these two equations. And this one. What do you notice about it? Why does one converge to a value when the other does not? Hopefully, you're seeing that the R value is making a difference. We're seeing that as the limit, as n goes to infinity, of a geometric series, t sub 1, of 1 minus r to the n power over 1 minus r, if you see that the r value is a fraction, it ends up just going, that fraction basically ends up going to 0. If you think about that logically, that n, that 3 to the n power, this number is going to get exponentially large, and then your numerator, well, 1 to the n is always going to become 1. So this is really just going to 0. So you have 1 minus 0. So when you take the limit of this, it ends up going to t sub 1, and then since this part just becomes 0, you are left with 1 over 1 minus r. Okay? So you end up getting this if your absolute value of r is going to be a fraction, less than 1. Okay? Your r sub n is going to 0. That's what it's saying. Okay? All right, so let's go ahead and apply that to a few problems. Let's take a look down below. You see just the general statement that we just said, t sub 1 times 1 over 1 minus r. If r sub 1, or if r is greater than 1, then the series will diverge. That's what we saw in problem number 1. If r is less than 1, then we know that the series converges. All right, so let's go ahead and try a few problems. 1 minus 1/2 plus 1/4 minus 1/8. The signs are always changing. That must mean we must be multiplying by some negative value. Negative times negative gives us positive. Positive times negative gives us negative, and so on. And so we see here we're multiplying by -1/2 every single time. Multiplying by -1/2. So if that's the case, we know our r value is going to equal -1/2. The r value, the absolute value of that is definitely less than 1. So we know that our series converges. If the series converges, let's go ahead and find that sum then. The sum is equal to t sub 1 times 1 over 1 minus r. T sub 1 is 1, right here, our first term is 1, times 1 over 1 minus r. r is -1/2. So 1 minus -1/2 that will end up giving us 1 plus half. So that's really the same thing as 1 over 3 over 2, which is the same thing as the sum of n is going to equal 2/3. Okay. If you need to pause or rewind, just ask the sub. I'm sure they will do that. Okay. Let's go ahead and take a look at our next one. Here's number 4. Let's try another one. Let's find the sum of this series going from 1 to 0.1, 0.1 to 0.01, and so on. The pattern you see there, we're multiplying by 0.1 each time, 0.1, 0.1, 0.1. We're multiplying. And so we see this r value is 0.1. Well, that's definitely less than 1. So we know, again, this series is going to converge. So let's find that sum. The sum of the nth term is equal to the first term being 1, times 1 over 1 minus r. Our r value is 0.1. So finding that out, we get 1 times 1 minus 0.1 will just give us 0.9. And 0.9, that's the same thing as 9/10. So 1 over 9/10, that's the same thing as 10 over 9. Okay. Again, pause if you need to, rewind if you need to. Let's take a look at the next one. So we've got 1, 1.1, 1.21, and so on. See if you can see that pattern. What are we doing there? Well, to get from 1 to 1.1, you're multiplying by 1.1. 1.1 times 1.1, that's 1.21. Hopefully that's obvious. You see 11 times 11, that's 121. Okay, so we're always multiplying by 1.1 each time. So we know that the r value, that's equal to 1.1. Well, that's actually greater than 1. So if it's greater than 1, it's going to diverge, which means we can't actually find that sum. That sum, just taking a look at it, you know it's going to go on to infinity. Okay. All right, so let's take a look at our next problem. 1 plus 3x plus 9x squared. Okay, so this problem's a little different because we do see an x value, but let's take a look at what's happening here. We can still see that the series is still doing something. We've got 1 plus 3x plus 9x squared plus and so on and so on. We're looking for the interval of convergence. We've got an interval, meaning we're going from some value to some value. So there's going to be a range of numbers that we're going to be finding here. That's because we've got this x value. We don't know what that x value is, so it can be a variety of numbers. So to find that interval of convergence, we just think, how do we go from term to term? It looks like we're going to be multiplying by 3x each time, times 3x, times 3x, times 3x. So we know that the r value is 3x. Well, we said that we want that r value, the absolute value of that, to be less than 1 in order for it to converge. So if the absolute value of 3x is less than 1, that must mean that the absolute value of x is less than 1/3, which means absolute value contained within 1/3 must mean negative 1/3 to 1/3. That's going to be our interval of convergence. That's letter A. For letter B, we just find the sum. So we know it converges, so we just plug it back in. The sum, as you go to term n, is just going to be, first term, 1 times 1 over 1 minus our r value. Our r value is 3x. So that 1 is just a little bit unnecessary. This just becomes 1 over 1 minus 3x, like that.